Hello, everybody. Welcome back to the seminar series on the Thorne calculus, a process calculus that is used in IHK to verify properties of consensus protocol implementations. So, to remind you a bit of where we are and what the goal is, so we want to have these consensus protocol implementations verified, and we picked this custom process calculus that we have developed here at IHK because there were some options of other process calculators that we considered, but in the end we concluded that it was best to come up with our own one. But it's a general purpose calculus. It's not tied to blockchain consensus protocols in any way. So it's generally good for concurrent and distributed systems. And as any process calculus, it has a precisely defined semantics. So, and an interesting thing about a process calculus, just as a reminder, it's an embedded DSL, which uses higher-order abstract syntax, HOAS, which means that all the issues with local names can be deferred to the host language, which is Isabelle here in our case. And it makes our job much simpler, but it also includes a few complications or challenges. And to this we will get when we look at the actual protocol implementation. However, we are not yet there. So as I mentioned in the past, the implementation in Isabelle whole, the proof assistant and its support for higher order logic, consists of two parts. The second part is the actual calculus. We call it the Thorne calculus, as I have mentioned, where Thorne is this nice letter which comes from the runic alphabets and is used these days still in Icelandic. And it's like pronounced like the English TH when it's not voiced, by the way, so that you know what this is for. English had it in the past as well, but they dropped it. So, however, we are not yet here, but we are here because we have developed the transition system framework. So our semantics of the process calculus, where we describe the behavior of processes, they are given as label transition system, where we have states and transitions, and the labels at the transitions, they are actions. So it's an edge-labeled graph. But actually, it's not just that we have a single semantics, but we have multiple. So as it's custom in process calculi and related systems, you distinguish between strong and weak semantics, or later between strong and weak by similarity. So this is the distinction people made first, right? We have this notion of bisimilarity, where two processes are bisimilar then if they behave the same in a certain way. There are two general variants of bisimilarity: the normal one, strong one, and the weak one, where the weak one ignores certain internal actions that are not observable from the outside. And in our case, like usually, these are internal communications. So now you can define weak bisimilarity separately from strong bisimilarity, but you can also do a nice trick and say, okay, we just define strong bisimilarity, the actual bisimilarity, and then for our label transition system, that is our semantics, and then we just derive from our label transition system another label transition system. And we can do this in such a way that if you just take the normal strong bisimilarity notion for this derived label transition system, then we get weak bisimilarity. So we take our actual transition system, derive a so-called weak transition system, and then bisimilarity for the weak transition system is just weak bisimilarity. And there are actually other variants in other directions of bisimilarity. So we, for example, consider a notion called asynchronous bisimilarity, where the normal bisimilarity is synchronous. And so in the end, we want to have four different notions of bisimilarity: the strong synchronous, the weak synchronous, the strong asynchronous, and the weak asynchronous. And often, if you look at the literature, you see asynchronous bisimilarity is defined in a quite different way, and then you wonder, okay, then we cannot reuse anything from our developments for bisimilarity and related things. But however, it is also possible to derive again a transition system from the original one, such that the normal bisimilarity is just, for this derived system, is just the asynchronous bisimilarity. And so the bottom line is that already in our calculus, we don't have a single semantics, but at the moment we have two, strong and weak synchronous, and we want to get to 4 of them, or we're actually in the process of doing so. And so already here we have 4 different notions of bisimilarity and 4 different notions of behavior, so to say. And we want to reuse as much code as possible. So we have this general framework for transition systems, and then instantiate it for our different transition systems, which are our different semantics. But this way, we have this general framework that is also usable for our process calculi in principle. And most of the framework, as I mentioned before, is not even tied to process calculi, because at the core label transition system just is this graph where the vertices are considered states and the edges are transitions. And so every description of some system that evolves or behaves in a certain way by executing actions can be modeled as a label transition system, and our framework works for it in principle. It's just that this last part about the context, this probably only really makes sense for systems where the states correspond to processes, where processes are some terms and programs, that the way we have a term structure. However, maybe also even this can be generalized. We will see when we get to contexts that I have already generalized things there a bit, because it turned out that this is possible without losing anything. It actually makes the formulation in Isabelle or generally in mathematics simpler. So I'm not even sure whether it's really tied to process calculi. So where are we? We are actually here in this part, up to methods. So we've seen bisimilarity already. So to remind you what it was, we have seen this nice diagram over and over again. So it describes what a simulation relation is. So K is a simulation relation if we have the following: if it relates to processes P and Q, or states P and Q, and we can transition with some action alpha to P prime, then there must be a Q prime such that we can transition here, and the resulting things are again in relation K. So, and I showed you how I phrase this just with relation operations and relations. So I said, okay, if you have the compound relation, the composition of K inverse, so going from the Q to the P, the composition of K inverse and transition with some alpha, then this is a subrelation of transition with alpha and K converse. We just express this property by a composition of conversion, and also with composition and conversion and subrelation relation. So, and also what was important in the general case, this arrow above here and this arrow below here, they can refer to different transition systems. So one is the original transition, one is the simulating transition system. So, and what's bisimulation? Well, this is bisimulation is K if we have the kind of opposite thing, so, or not really opposites thing, symmetric thing, so if P and Q are related, and we can make a step in the actual original transition here from Q to Q prime, then there must be this simulating transition to his P prime, so that we are in relation K again. And as I showed you, you can just say K is a bisimulation relation if it's a simulation relation, and the converse of it is also one simulation relation. And then bisimilarity, our notion of behavioral equivalence, is just the largest bisimulation relation. So it just requires us that if we can make a step on one side, we can simulate it on the other side. And then again, if you can make a step on one side, on any of the sides, we can simulate it on the other side, and so on and so forth. And because bisimilarity is the largest bisimulation relation, we have this kind of immediate method to prove that two processes P and Q are bisimilar. We just pick a relation K that relates these two processes. For example, we want to prove a lemma like P parallel Q, and maybe our Thorne calculus is bisimilar to Q parallel P. Then we must come up with a relation K that relates processes of this shape with the, of course, or okay, that relates two processes definitely if one of the process has the shape P parallel Q and the other one is then Q parallel P. So for any P and Q, this must be in relation K to this. And then we must check that if we make a step on one side, we can also make a corresponding step on the other side. And the resulting processes are again in this relation K. So preferably they should be again of this form P parallel Q and Q parallel P. However, this doesn't always work out. So it can be that there is maybe some additional stuff around this P parallel Q or in Q parallel P, or that we get into processes that are almost of this shape, but not quite, but they are just bisimilar to these processes. So we don't necessarily have the form of processes that we started with. And this means if you use this proof technique, we must extend our K to also cover these pairs. However, if we extend our K to be more permissible on the right-hand side here, then we also have to extend it, enlarged K on the left-hand side. So we must consider more pairs of processes P and Q. And so just a remark, so this P parallel Q here is this P, right? And this Q parallel P is this Q. So don't get confused by me using the same names here. So the point is, if we extend the K to be more permissible here, then we have to consider more pairs here. So we have more work, and also we can get even more pairs P prime, Q prime on the right-hand side. So we must again extend our K, and so on and so forth, which means that we might have to blow up our K quite drastically and handle lots and lots of more types of pairs, when actually these additions to K are maybe kind of boring, and they can be handled in a mechanical way and are maybe handled the same way in each and every proof. And in fact, this is typically the case. So what we want to do is we want to get rid of this mechanical stuff, of this boilerplate stuff. And the solution is that we say, okay, we don't require this P prime and Q prime to be in relation K, but in relation f of K, where f is a certain function on relations. And then we want to be able to conclude that if we have proved this, that the K progresses to f of K, so that we can play this bisimulation game where we end up in f of K instead of K, that then we can conclude from this that K is still included in bisimilarity, so that P and Q are in the end bisimilar. And for certain functions f, this can be done, this can be concluded, and this is what we want to look at today. So the idea is that this proof technique, this up to f, enables us to keep our K small. We don't have to blow it up, but we can ideally just stick to the pairs of processes that we are actually interested. For example, if we want to prove commutativity, then we are only interested in the end in showing something for P parallel Q on the one side and then Q parallel P on the other side. So ideally, we are able to reduce our K to just these pairs of processes and tweak or choose our f such that the processes P prime and Q prime we get into are in this relation f of K. And at the same time, this function f is a sound function, sound for this up to proof method, which means that from proving this here, we can indeed conclude that K is in the bisimilarity relation, and is tilde here. So, and we have seen not a necessary, but a sufficient condition for F being sound, and this is F being respectful. So respectfulness was defined like this. Function F is respectful here. If and only if for all relations K and L, we have the property, if there's a shortcut progression from K to L, and there's a shortcut progression from Fk to Fl. So what's a shortcut progression? Well, progression is the general form of this, right? So we have this kind of bisimulation game, but here we have K, here we have L, so they may differ. Then it's called that K progresses to L. So there's a unilateral and a bilateral. Was it bilateral or bidirectional? Oh, I don't even remember that. Lateral, yeah, I wanted to say that. So what we are after is sort of bilateral progression, but actually not just bilateral progression, but the shortcut progression is a bit more involved. It's this squiggled arrow. Shortcut progression means inclusion and bilateral progression, where as we have seen here, the inclusion is also a bilateral progression just for a different transition system, namely for the transition system, not the original one, but a transition system where we can make a transition from any state to itself using any action. So where we just do nothing, basically. So in shortcut progression means that we have the progression with respect to this shortcut system where we don't really step. And we have also the progression with respect to the actual transition system. So, and then we have this combined shortcut progression, and F is called respectful if it preserves, so to say, this progression relation. So if K progresses to L, then Fk must also progress to L. And today we will look at why this guarantees us that proofs up to bisimulation are sound, meaning that if you have proved this here, the K and F of K, that K progresses to F of K, and F is respectful, that then we have actually shown that K is in the bisimilarity relation, and so P and Q are bisimilar. That's the main thing for today, this showing that this is sound, not what I've done so far. However, there is a nice subsection here which concludes this respectfulness. No, it's not this subsection. Wait. This is what we had. So we have seen that certain operations preserve respectfulness. But this is the final subsection which I haven't shown you last time, before we get to the actual up to methods. It's about respectfully transformed bisimilarity. This is something interesting I discovered, which is maybe not too, it's not really complicated. Maybe people have discovered it before. But then again, I haven't seen it in the literature previously. And it is very interesting because it allows us to remove yet more boilerplate. So let me show you what this is about. It says that if F is a respectful function, then F applied to the bisimilarity relation. So now it's not just some relation K, but it's this largest bisimulation, the bisimilarity relation, right? So if you apply F to its bisimilarity relation, then this, what we get, is included again in the bisimilarity relation. So why is this? So we see here the proof, and now we can look a bit into this in more detail. We say, okay, from the fact that F is respectful, which we assume, right? So it's basically implication that we prove. Respectful F implies this thing below here. You can see it. If you go with the cursor of the QED, that it's indeed a implication. So this is just this outer syntax, more verbal description of this fact. So and also this description this way has the consequence that this implication is not the goal we have to prove, but it's only the conclusion that we have to prove, and we can feed in the premise as a fact. So it's already split up for us, so to say. And we say, okay, from this respectful F, from this assumption or premise, I think the Isabel terminology is actually assumption. A premise is exactly what's to the left of an implication arrow. And if we don't write it as a single implication, but we separate the assumption from the conclusion, then it's actually called an assumption, not a premise. But never mind. So from this respectful F that we assume, we can first conclude that F applied to bisimilarity is a bisimilation relation. And why is this? Because of this lemma. Bisimilarity is bisimilation. And now we can place the cursor here, and then we actually see what this lemma is, so we don't have to scroll up in our text. So as you might expect from a prover IDE. So by saying from this respectful F, we conclude something. We have respectful F as a so-called chained fact, a fact that we can now use in our proof of this first step. And this bisim tilde, this is just this bisimilarity is a bisimilation. And why does it follow that F applied to bisimilarity is a bisimilation? Well, because of what respectful means. So respectful F means that from K progresses to L, we can conclude F of bisimilarity, F of K progresses to F of L. But now we just specialize K and L to bisimilarity. So we know if bisimilarity shortcut progresses to itself, then F of bisimilarity shortcut progresses to F of bisimilarity. Right? So, and bisimilarity progresses to itself simply because it's included in itself, trivially, and it also bilaterally progresses to itself, so ignoring the shortcut. So again, shortcut was inclusion and this ordinary bilateral progression. And bisimilarity progresses to itself by means of this bilateral progression, because this is exactly what it means to be a bisimilation relation. So we have this here. So K is a bisimilation relation if and only if it bilaterally progresses to itself. Right? So this was progression K and L, and if L equals K, then we get this here. So this means that here we are. If F is respectful, well, and we know that from this lemma here, that bisimilarity is a bisimilation relation, then it shortcut progresses to itself. So we can apply this respectfulness, which means, okay, if it progresses to itself, then F of bisimilarity progresses to itself because of this preservation. And so F of bisimilarity must be a bisimilation relation, because progressing to itself is, again, a shortcut progression, but this includes the normal bilateral progression. And so F of bisimilarity progresses to itself. So F of bisimilarity is a bisimilation relation. Okay, so we have this here. Then we can say then, and then means just we take the previously established, the previous facts that we have established, and this becomes our next chain fact that we can use in the next step, what you might expect from then. So it's like the normal mathematical reasoning. From this, we have this, and then, so taking the result of a previous step, we show the thesis, and the thesis is our ultimate thing we have to prove. It's this one. So if we say show thesis, it's just an abbreviation for show blah, 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 what's here behind the shows. And this is what we see here. And why we can show this? Well, with the lemma that we have established, bisimilation in bisimilarity. So this here above said, this one, that bisimilarity is itself a bisimilation, but this is, so to say, the other one. Every bisimilation is included in the bisimilarity. So if F applied to bisimilarity is a bisimilation, and according to this lemma, from from K being a bisimulation follows K is included in bisimilarity, well, then this is included in bisimilarity. Simple. Yep. So, any questions to this point, perhaps?
Would you mind maybe turning on your line numbers, please, again?
For some reason, they are turned off. I really don't know why.
Okay, thank you.
Bizarre. Maybe this doesn't survive the restart, but it's kind of awkward.
Ah.
So, can you remind me where the line numbers were? It was here.
I think it's just, yeah, toggle line numbers, yes.
Okay. You wanted to refer to some line, or just generally have the line numbers?
Yeah. So I didn't quite get it why we needed to have the bisimp again in line number 193. Is the using? Why should the using not be enough?
Well, if you have proved this, right, that F applied to bisimilarity is a bisimulation, and we additionally use this lemma that we can conclude from case bisimulation we have this, then we can make this step. And that we have written this, you mean that why we need this, right? Is this what
no, I was wondering why just having line number 192 is not enough, and we.
Well, if you only have line 192, then it just says if K is a bisimulation relation, then K is included in bisimilarity. But we can but to prove that F applied to bisimilarity is in bisimilarity, you must know that F applied to bisimilarity is a bisimulation relation in order to apply this implication.
So it's kind of doing instantiation?
Nah. The point is, so we want to apply this implication, but we apply it to some concrete premise, namely that F applied to bisimilarity is a bisimulation relation, this one here. So this is
right, okay.
And in this K is instantiated to F applied to bisimilarity, right. And then we get F applied to bisimilarity is included in this here.
I think Cosine's question has to do with why we need the simplifier and not using something like by-fact, bisimulation in bisimilarity. I
thought Cosine wanted to know why we need to state this in addition. But in a sense, we don't do. In the proof text, so I said from respectful F, we have established this, and now that we have it, we can then say, by just adding this lemma, so to say, we can conclude our thesis here. However, technically, each proof step is separate, right? So you get some facts and then apply some proof method like the simplifier or something more fundamental, and then you get your statement proved. Now this then suggests, and this is really its purpose, that we just go on with our proof and we can basically use what we have proved before. But technically, this part is still, in a sense, separate from this part. You must list all the statements, all the established facts that you are using here in this part, and then you can prove what you want to prove. And the then just means that you take what you have proved in the previous step and feed it into this next step. So it now occurs here. The IDE shows us that we pick this fact that we have proved previously, but we don't have to explicitly write it in the text. This is the then. So then says that we take this thing and feed it here. So if you would remove the then, just say show thesis, then we would here have only this lemma that we use, but we wouldn't have what we have proved in the previous step. And by saying then, we get it, and then we can conclude from these two this. I don't know, is this what you, does this refer to what you wanted to know, Hossein?
Well, yes, it does speak about it. I was more concerned about why just mentioning line 192 is not enough, and you also responded to that question, but you also responded to, or you also gave us more understanding about the general line of reasoning.
Yeah. Okay.
Yeah. So thank you.
More questions?
Yeah, I think he was referring to why there's the need to use the simplifier and not using the fact or rule by simulation in by similarity.
You could do something like that. You could say, I take by simulation, for example, I take by simulation by similarity, and then I apply it, and this is what is off, what I'm writing now is for. I apply it to this thing here. So I could remove this and take this guy. And then it would take this lemma. This is a kind of fact expression. I can take an existing fact and kind of tweak it a bit. So I take this existing fact and apply it to what I've just proved here. And this way, this implication is kind of applied to some concrete premise. And by this way, this, one moment, this K, what we had here, is instantiated, because it must be instantiated to this guy here. And then we directly get what we want to prove. And then I can just conclude the proof with a dot, because what we want to prove is already here. And then it also works. However,
right.
This is what you wanted to know. Okay, now I see. Yeah, so you can directly have some simple forms of tweaking facts via these proof or fact expressions. And this is possible. It's just kind of seemed too low level for me, or so. So I used the simple.
Sure. I mean, I think
I generally prefer to go more low level if this is what's necessary, to not give the impression that you need some advanced reasoner when you actually the thing is very simple. But in this case, I avoid a bit these proof expressions, these fact expressions.
Yeah,
it looks so nice to me, but you can do it. Yeah.
Yeah. I mean, I can read this proof. Well, provided that I did know the syntax of, but I can read this one better than the previous one, although I understand that when you have grown the necessary skills, then it's kind of obvious to you, and you don't need to be that explicit about the instantiations.
Yeah, so this is really a corner case, I would say. I can see something good about both approaches. I mean, what I don't like so much about this approach is that you have to specifically refer to this fact when actually I think it's a nice thing to have this then, so where you just refer to the previous fact, because this is a bit what mathematicians are used to, right? I establish this, and then from this follows this, and from then follows this. You often have these sequences of implications that you kind of chain together. And
sure, but you also do some sort of numbering that you can say, okay, I'm applying this previously proved lemma to this particular relation.
You can actually do this.
There is that kind of referral.
You can say, for example, this is 1 or this is star or so, and then you can just say of star here. This also works. So
I like this one even more.
I typically tend to not do it because, I don't know, my rationale is somehow, if I have many of them that I need to refer to, then I have all kinds of stars and whatever not, and I rather just spell out the proposition, at least if it's short. If it's long, then I like to do something like the star or give it a proper name or so. But I think this is a point where, for example, Javier disagrees. I think, was it you, Javier, who didn't like me so much doing, one moment, who didn't like me to do something like this here, right? So but it's somehow my style. Most of the
Yeah,
time,
that's-
Sometimes I used the facts.
no, I remember it wasn't you. It was someone else. I gave a talk at the university here in Tallinn, Estonia, at the University of Technology, and there was also some person who uses Isabel, has been using Isabel a lot, and he very much disagreed about this style, I think. So he really was rather pointing me to this star thing and so on. But then again, this style that I originally used, this has the advantage that you can have this sequential reasoning, right? Then, and then you refer to this one.
Yeah, thank you.
Okay.
Sorry, a last remark. And with that style, using the then, you need the simplifier to substitute the schematic variables for the chain facts, right? That's why we need the simplifier.
Yeah, I'm not really sure if the K would be instantiated if Isabel could figure it out without this simplifier. Maybe. I think you cannot say something like rule also. No, that doesn't work. So I'm not particularly sure about the really technical details here. So in cases like these, when I think, okay, does it work with some more primitive proof method or so, then I just sometimes just experiment. I just write rule, blah, 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 or fact, also these primitive proof methods, and just see whether it works. And here I use the simplifier, but it's maybe slightly misleading if you look at this proof method, because it suggests that you need actually some rewriting, which you don't.
Right.
It's very, very primitive.
Right. By the way, what is that OF for? Is it just of, or is it you stated it that that's a fact? So I'm taking that OF is an abbreviation. Is that?
No, OF is just the word off.
Oh, I see. Okay, but they are referred to as facts.
This premise also, right? You say off and then a fact that's used as your premise.
Ah, so the fact is what comes after the off.
Yeah.
Right.
Now I messed up my history. Sorry. Okay. So if I write something like off star, right? And the star is the fact, and this off is part of the syntax. Or no, this is an attribute. This is the general thing.
Okay.
You can write attributes in the brackets. An attribute can modify the fact. So it's more like an application expression. And the off is then part of the syntax.
I see. Okay, great. Thanks.
Okay, so we have now established if we apply a respectful function to bisimilarity, then it's included in bisimilarity. And this has not really to do with what we use respectful functions for, because we want to use it for up to methods. But this is a nice sidetrack, which I've discovered, and which is extremely useful for us. And why is this? So let's check what this means. So what are typical respectful functions? So a typical respectful function is this constant bisimilarity, right? Where we can apply our function f, which is now this one here, to any relation k, and we always get bisimilarity. But what does this lemma mean for this? If we apply f to bisimilarity, and f is now our constant bisimilarity, then we get bisimilarity, and then this lemma just says bisimilarity is included in itself, which is of course trivial. So it doesn't give us anything for this small case. Another respectful function is the identity function. So identity applied to bisimilarity is bisimilarity. So again, it says us that bisimilarity is included in itself, and that's not useful because we know it anyhow, that any relation is included in itself. And then we have this composition. This respectfulness is preserved by composition. And from this, for example, we can derive this bisimilarity up to bisimilation up to bisimilarity, right? So this is also a respectful function. It looks like this. I've mentioned this several times. So This is when in our bisimulation game, we start with something being in relation K, but the processes we produce by means of these transitions, they are allowed to be in this enlarged relation. So they don't have to be directly in relation K, but they can be two processes that are just bisimilar to something that it's related by K. So does this maybe give us something interesting for this lemma here? So this is respectful. And if we apply it, so this is now our function f. And if we take this to be our function f and apply it to bisimilarity, then we get bisimilarity composed with bisimilarity composed with bisimilarity. And since bisimilarity is transitive, it's again just bisimilarity, or it's something that's included in bisimilarity. Actually, it's because it's sorry, because it's reflexive. It's even equal to bisimilarity. So it again gives us bisimilarity inside bisimilarity. So you might wonder, why is this lemma useful at all? Isn't it just a triviality all the time? But actually, it isn't, because later we will have up to context. And let's now look at some concrete example to make it more easy to understand and to make it more easy for me to describe. If we have something like up to parallel context, for example, where we say, okay, if something is related in K, then we get to some P prime and Q prime that are not directly related in K, but they have some common context. And in this case, a parallel context, it always says some P parallel to blah, blah, blah. And only this blah, blah, blah is what's related in K. So to make it precise, our F is now something that when applied to K gives us a relation that takes, so it's a function to the Booleans, it takes two processes S and T, and enforces that there exists, I think I have to write something else because this syntax I will be using is not defined. So F applied to K is a relation that can be applied to two processes S and T, and it's true if and only if the following holds: there exists Q and R such that S equals P parallel Q, where the P is somehow fixed from the outside. So the F is for some particular P. And the T is P parallel R, and K relates Q and R. So the two processes that are related by F of K, they both have this, respectively, this shape. So they are both parallel compositions that share this process P. And on the right-hand side, they may differ. One has Q, one has R, but these are the ones that are in relation K, as can be seen here on the right. So it's not really that these processes that Fk relates are in relation K, but these are two processes in relation K extended by this common context. And this is something we have quite often, for example, in our proofs of network equivalence, so equivalence between broadcast and certain forms of peer-to-peer communication, where we forward data and we read the data packet and we forward it, and then we can already start to read the next data packet. We have certain recursive definitions of this forwarding, where at every step we have an additional process that sends just the previously received packet, and this is then our P. And we don't want to handle the fact that there is also this P process around, but we want to be able to concentrate on the Q and the R, and this P parallel blah, 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 that this is there in addition. This should be handled generically by our up to context proof method. So, and this is now a very interesting relation, because look at what happens when we go to this respectful F implies this guy here. Now it gets more interesting. F, what is F applied to bisimilarity? Let me develop this here. So F applied to bisimilarity is, well, now we have to just insert this here. This relates to processes S and T. If S is P parallel Q and T is P parallel R for some Q and R, and Q are bisimilar to R. And now what does it mean that this is included in bisimilarity? So this is now included in bisimilarity. Well, we can expand this. So this relation on the left is included in this relation on the right. This means that for all processes S and T, if you apply this on the left, this implies the thing on the right. So let's take this thing on the left and apply it to some concrete S and T. And just remove the lambda. This implies this applied to S and T. But then we can write it in fix. Say this. So if there exists Q and R such that our S and T have this shape, and Q is bisimilar to R, then S is bisimilar to T. However, if there exists some Q and R such blah, 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 this implies this, then we have this existential thing on the left-hand side of an implication. So we can actually make this a for all and put the parentheses like this. So for all Q and R, we have the statement that if S equals this and if T equals this and blah, 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 then we have this. And since universal quantification is implicitly in place, if you have free variables, you can just write it as this. So if S is this and T is this, and we have this bisimilarity, then S is bisimilar to T. However, if S is equals this and T equals this, then we can just replace the S and T here on the right-hand side by this, and the T by this. And since the S and T are not used anywhere else here, we can actually remove these conditions because S and T have now become uninteresting. And then we get this, and this is what people call a preservation or congruence law. This means, so it says if Q is bisimilar to R, then PQ is bisimilar to PR. And so if you replace a subprocess to the right of the parallel composition by something bisimilar, then the resulting processes or the processes that we started with and the resulting one, they are bisimilar. And this makes our equivalence relation bisimilarity, this tilde, into a congruence with respect to parallel composition. And that's highly important because this allows us compositional reasoning. So if you have a system that's composed of several subcomponents via the parallel composition operator, then we can just reason for one component. Okay, if you take this component and replace it by another component, and then we can prove that these are bisimilar, then we know the overall system also stays bisimilar. And therefore, we can do reasoning in a modular way. So we definitely need this lemma, and there are similar lemmas for other operations other than parallel composition. And for parallel composition, it actually holds on both sides because parallel composition is commutative. So we can immediately derive that we can that if you replace something on the left-hand side by something bisimilar, then it's also we also get something bisimilar. And that's extremely cool because this respectfulness, this is only there initially for getting up to sound up to context proof methods. Then there's a certain form of respectful functions which are for up to context proof methods. But now we see they are not just useful for this up to context proof methods, but if you have established the respectfulness of such a function f for up to context, then not only we get the soundness of up to context, but we get also, by this little lemma, our preservation laws, and we don't have to prove them explicitly. And they are not always so easy to prove, so it's quite a bit of work. And surprisingly, this notion of respectfulness that we have for these up to methods allows us to immediately conclude that these laws like this here, hold. They're extremely useful, in particular, because, as we will see later, in our framework, if we have established the soundness of up to context for the actual transition system by proving certain fundamental properties, then by just proving two little additional properties, we immediately get the soundness of up to or the respectfulness of up to context for the weak transition system. And so we also get for free these kind of rules for weak bisimilarity. And before we had to kind of prove it separately for strong and weak bisimilarity. And weak bisimilarity, the weak bisimilar thing was similar to the strong bisimilar thing, but of course a bit different. And so there was a lot of repetition going on, and we can throw out all this repetition out of the window. We get these laws basically for free, and that's extremely cool. And it's in line with this general approach of this framework that we can really concentrate in all our further proofs on the essence and try to really avoid all kinds of boilerplate by having the right abstractions, like, for example, this notion of respectfulness, and having proved certain things once and for all so that we don't have to repeat ourselves. I should mention that I did not invent all these concepts. They are mostly from a paper from the 90s by some person called something like San Giorgi. I know that I pronounce it wrong. He's Italian, and I don't remember the precise pronunciation.
Yeah. Sorry, you are pronouncing it correctly. San Giorgi.
I think there was something. There is some issue with the G is followed by an I. Maybe he is pronounced like this very often, but I don't think it's correctly. I think there's a small twist. But anyhow, so he wrote this paper, and this, what I have here and show to you, this is largely a formalization of his paper, actually. But I have made some improvements and also some extensions, and in particular that we can go from strong to weak bisimilarity when proving the correctness of up to context. This is my contribution, and also this little lemma. This is something he didn't mention. So this is something that allows us to prevent us from writing a lot of boilerplate, and it's extremely useful. Any questions? So I see we are almost running out of time. I have not got to up to methods, but okay. But we have looked in detail at this stuff, which might be also interesting. Maybe let me get at least to the definition of up to methods, so that we have done at least something about this, and then the soundness maybe has to wait a bit. So what did we see before? We had this notion of progression. This was what we had in the diagram below here. And then we saw that this simulation by simulation and also the thing up to, these are special cases, but we haven't defined this one yet in the code, but only this one. So the unilateral progression was that if you can go like this and then like this, then we can go like this and like this as well. Bilateral progression is that we have a unilateral progression and a unilateral progression for the converses. And then we said, okay, simulation just means the relation progresses to itself. And bisimulation means it also progresses through itself, but now with the bilateral instead of the unilateral progression. And if you have simulation by simulation up to some f, then it doesn't progress to itself, but to f applied to itself. And this is what we have here. So these nice little arrows, these denote a subscript that can span multiple characters. So they are single character subscripts which are supported by the Isabelle IDE by really showing subscripts. These multi-letter subscripts, they are not supported. Multi-letter because this is not necessarily an F. It can be later any expression because this is an argument. So, but still they have some purpose, these arrows, because if you produce a PDF file via LaTeX, then these become really proper subscripts. So we define the notion of simulation up to. So this has two arguments. First is a function from relation to relation. This is this function f. And the second is a relation. This is this relation k. And we say k is a simulation relation up to f if and only if this holds, right? So we get a bool. And so as we say, okay, this is a simulation relation up to f. K unilaterally progresses to f of k. And likewise for bisimulation up to, which has then this notation with bisim and then the subscript f. And this means k bilaterally progresses to f of k. And then there's something very trivial. Of course, we have here...
Can I just ask a question right here?
Yes.
So what is the mathematics, or what is the LaTeX that you would want to be generated for line 282? So like is it a tilde and then subscripted by the curly f? Is
One
that
moment.
what you want?
Which line? This one?
Yes, 282.
It should look like this.
Okay.
And so it's a subscript.
Right. Okay, and then because you don't have the subscript, then you kind of work it out with those two, tilted arrows, right arrows and left.
So you see, I have a subscript here, but this is only for the single letter case. So how it works is
Okay.
sub, and this gives me this character here, this downward pointing strange arrow. And the IDE just handles this way. If I have this arrow and then it's followed by, for example, an F, then it's just put as a subscript, but it's two characters internally. And here it's, so to say, three characters, right? So this is a begin subscript and an end subscript, while this other thing here just say, okay, the next character is to be put as a subscript. So there are both these variants. This one with a single character is handled by the IDE. The other one is not handled by the E, but it is handled by the LaTeX output.
Okay, thank you.
So it looks a bit awkward here, but it looks hopefully great if you produce nice text. Okay, and here we already see that we sometimes need multiple characters in our subscript. So this states the trivial thing that a simulation relation is just a simulation up to identity, right? Identity to k is k. And this can be proved by the simplified. Merely just expands the definition of the sim and the sim up to, and then figures it out very easily. And same way for the notion of bisimulation relation. And yeah, so I think we have taken 1 hour. Are there any questions about this block here? Maybe I will quickly show you what to expect. So I'll give you a bit of an overview of what the structure of this soundness proof is. So what we do is we start with a definition of expansion. And if you take such a function f that typically will be respectful, then we define the expansion of it, which is denoted by this angle brackets f. And this is the union of identity and F. Why is this? If we want to prove that from this here, it follows that K is included in bisimilarity, it means that we must be able to play this actual bisimulation game forever. And here we progress from K to F of K, but we already have established that bisimilarity is the largest bisimulation relation. So if we find a relation K that is an ordinary bisimulation relation, so not up to something, which means that it progresses to itself, then we are basically done. Then we know K is included in bisimilarity. And our goal is here to take the K and the F and from them form a kind of master or big relation that is then an ordinary bisimulation relation. And I already sketched a bit what the problem is. We progress from K to F of K. So if something is related in K, then this resulting thing is related in F of K. So it's not quite K anymore. And now we have to also consider F of K on the left-hand side. And then we progress into something that is, we progress into F of K. And then we also have to consider this for the bisimulation game. And what we in effect do is that we take our K and blow it up to also contain certain nested applications of this function F. And this corresponds to what we would otherwise have to do by hand. So I said, okay, if we would not have this up to method, but would have to use this this simple way of doing bisimilarity proofs that you see depicted above here. And I said, okay, if you don't get from our actual relation into our actual relation again, but in something different, then we have to also consider it on the left-hand side, but then we get maybe into something yet more different, and we have again to consider it on the left-hand side. And what we now do in our soundness proof of up to F, bisimulation up to F, is that we basically construct this whole blown-up relation which considers all these things like K and F of K, and then these repeated applications of F intertwined with something else, actually. And then show finally that this is an ordinary bisimulation relation, which contains the K. So we come up with this notion of extension, which is this. So the extension of F applied to K is K union F of K, contains both what we had on the left and on the right. Then we show that this expansion operation preserves respectfulness. So if F is respectful, the expansion is respectful. And then we show the key lemma. If F is respectful and it's K is a bisimulation up to F, if F is respectful, and we have already shown, which we would do specifically then for later for different lemmas that we want to prove. So F is respectful and K progresses to F of K. Then we can somehow show that this master relation progresses to itself. And this is what we have here. Then we show that the union of all extension of F to the power of n of K. And this is this n times application of this extension F. So if we apply this extension F arbitrarily often to K and collect all these arbitrarily often applications, then this whole union progresses to itself. So it's a bisimulation relation. And this is the tricky part of the proof. But once we have this, then it's simple to prove that up to is sound. So if F and up to is sound just means F is respectful, and we have established that our relation K is a bisimulation up to F. So K progresses to Fk. Then K is included in bisimilarity. And then we can do up to proofs. And then there's only a bit more in the end. Then we have some little lemma for, or theorem for symmetric K. So if K is symmetric, then we can simplify matters a bit. Then we actually have to prove that's a simulation up to F, and not necessarily because that's a bisimulation up to F follows from that. And then we have certain rules, which are basically rephrasings of these two lemmas for the symmetric and the the general case. So these do not talk about these relations and relation inclusion anymore, but they break it down to this non-point free style and logical connectors. And this is important for using these lemmas in a quite convenient way using Isabel's co-induction proof method. But this is merely a technicality. This is nothing, so to say, substantial about the theory. And that's it for this theory of simulation systems, actually. So this concludes the general treatment of up to. And another thing that's the major thing afterwards is this up to context. Okay, questions? Okay, the next time we will finally look not just at the definition of up to methods, but also at this proof of soundness that I have just shown the basic structure. And thanks for listening, and see you hopefully next time.